Now let's solve some problems using the signals knowledge that we have learned so far. The first problem is we have to integrate this signal that is given here from minus infinity to t. So let's do this graphically. So you don't have to write any equations for this, you can just do this completely graphically. So let's first take this part, which is basically a step function, right. So what we have here is a step function plus delta of t minus 1 minus delta of t minus 1 minus delta of t minus 2 minus delta of t minus 3. This is the analytical expression of this entire plot. You can integrate this completely and then you can plot it also. But the nice thing is we can do this graphically as well. So if you integrate this step function, what are you supposed to see? You are supposed to see just a ramp, right. So it keeps increasing. This has a slope 1. So this has slope 1. So this is what you are supposed to see. Now if you integrate this step function, you get this ramp. If you integrate this Dirac delta signal, then what are you supposed to get? So if you integrate the Dirac delta signal, then you will get a step function. So this is the Dirac delta signal at 1. So similarly, there is another Dirac delta at 2, and there is another Dirac delta at 3. So now you have to add them up all. Let's see what happens when you add them up all. So at this point, the value of the signal is 1. So it increases from 0, hits 1, and then keeps increasing, but then you have to subtract 1 because of this Dirac delta. This is x of v dv. So subtract it. At this point, it becomes 0. Okay. Now, but then the signal actually keeps increasing. So it increases, and then once again it becomes 0 because of this Dirac delta's integral at 2. Then once again it keeps increasing, it becomes 0 at 3, and then at this point it starts growing once again. So basically what are you doing? You are adding this ramp with 3 different unit step functions which have an amplitude of minus 1, but at different time locations. Okay. So all you are doing is adding 3 different signals. The first signal is this ramp, second signal is a unit step function. So this is 0 which has value 1, and this has amplitude minus 1 from 1, and you are adding another one which is at 2 minus 1, another step function at 3 minus 1. So if you add all these 3 together, then you get the solution that we are looking for. So basically what have we done here? We have split the given signal into 4 different individual signals, integrated them separately, and then added up together. Right? So this is a nice way that you don't have to write analytical expression. Just by looking graphically you can draw what happens. So we have integrated the step function separately, gotten this ramp, integrated the Dirac delta, gotten 3 different step functions, just added up together. So if you add it up together, you will get this some kind of sawtooth pattern. So this is the integral that we are looking for. Okay, now we have another signal here. It's given that the signal that we are going to work with is cos 2t times u of t. What is the period of this signal? Let us draw this first. How does this look like? So, the signal is cosine signal multiplied with the step function. So, what is the step function? The step function is non-zero only for positive values of time. You are multiplying this with a cosine signal. So, what are you supposed to see? You are supposed to see something like this. So, this is the signal that is given to us. Now, what is the period of this signal is the question. The period does not exist because this is aperiodic. As you can see, the signal does not exist for negative values of time, which means that it is 0 here and the signal starts becoming non-zero only at t equal to 0. Clearly, there is no cycle, there is no signal existing on this side, which means if you shift it, you will not get the same signal for no matter what amount of shift you do. So, which means this is aperiodic. Okay. Now, what about its even part? How do you compute the even part? The even part is x of t plus x of minus t by 2. In this case, it turns out to be cos 2t plus cos of minus 2t times u of minus t by 2, but cos of minus 2t is just cos 2t. So, what is this signal? So, basically now we have u of t cos 2t and u of minus t. So, now we have the other signal that is added up together. So, what is the other signal? The cos of 2t times u of minus t. Now, that has all the signals in the negative values of time. So, we have this portion and this portion together. When you put them together, when you add them together, what do you get? You get a nice periodic signal. So, essentially the even part now becomes periodic. This is a nice example where the actual signal is aperiodic, but if you take the even part, it turns out to be a periodic signal. Okay. What about the odd part? So, the odd part is cos of 2t u of t minus cos of 2t u of minus t by 2. Is this periodic? This is not periodic because let us see how it looks like. So, the right hand side portion just remains as such, but the left hand side portion, because of this minus sign, flips sign here. It starts looking like this. Okay. So, there is a sudden change in symmetry here. So, this is the odd portion. Is this periodic? Clearly, it is not periodic because this portion is not a full cycle. You cannot get this in any other portion. So, this is aperiodic. The odd portion is aperiodic, okay, but the even portion is periodic. What is the period of the periodic signal? So, it is the cos 2t itself. So, the angular frequency is 2, which means period is 2 pi by 2, which is equal to pi. So, the period here that we are looking for is pi. Okay. Now, if somebody gives you a signal x of t and then says that I know the derivative of the signal x of t, and that is equal to, let us say, some z of t, okay, which is equal to some d by dt of x of t. What is now the relationship between the derivative of x of at plus b and z of t? How is this related to z of t? So, given z of t and x of t, can you find out the derivative of x of at plus b? It directly falls from our high school calculus. All you have to do is just say that if the derivative of x of t is z of t, then the derivative of x of a t plus b is nothing but a times derivative of x of a t plus b, that is it. Okay. So, basically you have to take derivative of x of a t plus b times the derivative of a t plus b itself, which is equal to a. So, this part is equal to a. So, you can write the entire thing as just a times the actual signal. Okay. In other words, this is equal to a times z of a t plus b. Okay. So, the derivative of x of a t plus b is a times z of a t plus b. So, the individual derivative also gets shifted accordingly and scaled accordingly, and then you just have to multiply a with that. Now, let us see if this is true for some example. So, let us take u of t. We know that its derivative is del of t, which is the Dirac delta function. Now, let us take some u of a t plus b. Now, this is a very interesting example because let us take a is equal to some 2 and b is equal to some 1. Okay. Let us take b is equal to a, let us take a equal to 2 and b is equal to 0. Now, plot this. How does this signal look like? Still looks like u of a t, still looks like u of t. So, intuitively, when you take the derivative of this, it should still be the Dirac delta function itself. So, that is our intuition. So, let us see if that is true here if we use these techniques. Here we are saying that the derivative is a times this Dirac delta, but then here we are saying intuitively if you take the derivative here, it should still be Dirac delta itself, right. Let us see if that is true, because u of a t looks exactly like u of t. So, then the derivative also should be exactly the same, which means derivative of u of a t should also be just del of t, which is the derivative of u of t itself. Now, what happens when you take the derivative of u of a t? It is, according to whatever we derived now, it should be a times delta of a t plus b. Okay. But we know that whenever there is a time scale, delta of a t is equal to delta of t divided by mod of delta. This is what we learnt in the properties of the Dirac delta function, which means here we have this is a times delta of t plus b by a divided by mod a. Okay. In other words, what do we have here? This is equal to sine of a times the Dirac delta of t plus b divided by a. Why did we get the sign? Because a, if it is negative, let us say a is minus 1. If a is minus 1, then you have a negative sign in this fraction. So, you can write a as equal to mod of a times sine of a. So, the mod absolute value gets cancelled. So, let us see what happens if a is minus 1 or a is minus 2. Let us see this case. So, if a is equal to 2, then this is the Dirac delta derivative. Intuitively, we saw this should be the case. Now, let us see with calculus why this should be the case. So, remember how did we derive the Dirac delta function? We said we are going to observe what happens in a very small interval epsilon, okay, and take the derivative of this signal. So, the derivative here apart from this epsilon interval is 0 everywhere. In that epsilon interval, it is changing from 0 to 1 in the interval epsilon. So, the slope is 1 by epsilon and we have this interval epsilon. So, as epsilon tends to infinity, we get the Dirac delta signal, right, and the area is 1. Now, when you take u of a t, what happens here? The interval gets squished, right. So, this epsilon becomes epsilon by a. The interval in which it increases from 0 to 1 becomes epsilon by a, which means the slope also here changes 1 minus 0 divided by the interval is now epsilon by a, and this interval is epsilon by a. So, now the slope is 1 by epsilon by a. In the interval epsilon by a, the area still turns out to be just 1, and exactly that is the reason why we still get delta of t even when we take the derivative of u of at. Okay. So, remember the derivative of x of at plus b is a times z of at plus b, but when the signal is unit step function, the derivative of u of at plus b is nothing but the sine times the Dirac delta function itself. Now, what if a was minus 2 here? So, if a was minus 2, what happens? There is a time reversal, which means you get u of, which means when you take the derivative, the amplitude of u of t decreases from 1 to 0, which means the slope would be negative, and hence you would get the Dirac delta in the negative direction, and so here we will get minus 1. So, that is exactly what is reflected by this analysis. This is a very simple analysis, but it helps us in many different ways in practice when we use it. Okay. Often we encounter this correlation coefficient in many statistical analysis and many times when we work with random signals. So, we will define here the term cross correlation as simply the area under two different signals. Okay. So, you are given a signal, let us say y of t, another signal x of t. How are these two signals correlated? How are they related? What is the similarity between them is captured by this term cross correlation. So, how are we computing it? We are saying that we will take the signal y of t and multiply that with x of t with a shift, with a small time shift for all possible time shifts. So, in this case we are multiplying the signal x with some time shift t, okay, and the signal y, and then whatever is the area under the product, you just call that as the correlation or the cross correlation for the shift value t. If t is equal to 0, then what are we doing? We are just simply multiplying x of t, y of t, and then finding the area under them, and t is equal to, let us say, 1. Then what are you doing? Then you are shifting x by 1 and then multiplying with y and then finding the area under them. Okay. So, this is what we call as the correlation. So, a signal which is highly correlated will have very large positive amplitudes for this cross correlation term. So, if r x y of t is a large value for all values of t, it means that the signal x and y are highly correlated. Okay. Now, you can set the signal y to be equal to x itself, then what we get is called as the autocorrelation. So, x, so that is denoted by rxx. Okay. Now, we will not go into the details of this cross correlation, probably you will learn that in a statistical signal processing course. We will now just see the signal properties of this cross correlation, because there is rxy and rxx, they themselves are signals. So, we will just see the properties of these signals. We will see the properties of cross correlation and autocorrelation as a signal. Okay. So, given these two signals, can you find a relationship between them? So, remember we said rxy of t is nothing but r of t plus v minus infinity to infinity y of v dv. Now, let us say that sum s is equal to t plus v, then we will have minus infinity to infinity x of s times y of, what is v? V is now minus t plus s minus t plus s, and ds is just dv because t is just a constant, ds. Now, if you look at this expression, this is exactly the expression for ry of x, this is exactly the expression of ryx for minus t. So, the relationship between Rxy of t and Ryx of t is that they are time reversed versions of one another. So, if you time reverse Ryx, then you will get Rxy. So, you do not have to compute these two signals separately, you can just compute one of them, time reverse them, you will get them. Okay. So, the nice part is that even if one of these signals turn out to be an even signal, then both are equals. So, let us say Ryx of t is even. So, if Ryx of t is even, then we know that it is equal to Ryx of minus t. So, if one of the cross correlation terms is even, then Ryx is equal to Rxy of t. So, both these cross correlation terms become equal only if they are even. Okay. Now, we will talk about the properties of the autocorrelation term. So, what is the autocorrelation term? The autocorrelation term is simply substituting y is equal to x. So, just substitute y is equal to x here, then you get Rxx of minus t equal to Rxx of t. All we did is just substitute x instead of y here. This automatically tells us that this signal is even. So, the autocorrelation of any signal is always an even signal. This is a very nice property to use for statistical analysis. Okay. Now, the third question is, what about the periodicity of the autocorrelation if x of t itself is periodic? So, what is the autocorrelation? Autocorrelation is x of t plus v times x of v dv. Now, let us assume that x is periodic, which means x of t plus some v is equal to x of t. Now, if x is periodic with period capital T, then we should be able to add anything here, right. So, any value here, and when you add the period to it, it should still remain the same. In other words, we can write this as this small t as some s plus capital T or s plus n capital T, right. So, we can write any given small t as s plus some n t, where s takes a value which is between 0 and t. So, once you can write something like this, then we know that for sure this is exactly the same as x of s plus v times x of v, right. So, what are we saying here? So, we are saying, what are we saying here? So, we are saying Rxx of s plus nt is equal to Rxx of s. In other words, we just proved that the autocorrelation is also periodic with period t. So, if x of t is periodic with some period t, its autocorrelation is also periodic with the same period. So, this knowledge of the properties of these signals helps us analyzing the statistical property of these signals. So, later when we want to know, let us say you feed in an input and you get an output, you want to know how much of the input is present in the output, or you want to know the relationship between how close is your output to the target output that you are looking for. So, for these scenarios you would try to find out the correlation between the output and the target that you want. There you will use these correlation properties, and then when you correlate it, you get another signal. So, essentially you can see this as getting a different signal which captures the relationship between two other different signals, and that tells how these two signals are similar or dissimilar, and these properties of periodicity and symmetry helps us to analyze that. For example, if the autocorrelation is periodic, then it tells us the signal is similar to itself at certain periods. That exactly is what it means by periodic signal, right. So, if you shift it by some period, it looks exactly the same. So, if the autocorrelation is periodic, it means that After a certain period, the signal looks exactly the same. It is exactly similar by this amount. That is what is captured by the autocorrelation value.